Welcome to the third of 7 videos covering quadratic theory for higher maths. This video is going to focus on max and min values of a quadratic. So, learning intentions. I want you to understand how and be able to identify the maximum or minimum value of a quadratic function. So, in standard form for a quadratic, y equals ax squared plus bx plus c, it can be difficult to spot the maximum value of the function. What I mean by that, I put in bracket y, maximum value is the y value of the function. Whatever y value of the function is considered, the max or min. So we're going to go looking for that. Now, what we're dealing with in terms of quadratics, the max and min will occur at the turning point. Now, both won't occur at the turning point. It'll either be one or t'other, depending on what type of quadratic you have, and obviously that will be dependent on the quadratic function that you're given in algebraic form. So for max turning point, that'll occur when you have a negative x squared quadratic, and a minimum turning point when you have a positive x squared quadratic. So depending on which type of one will depend whether you're being asked to look for the max or min. Because remember, if it's a maximum turning quadratic, the minimum value will be infinite, because it never ends. The two sides, either side of the turning point, go off to infinity. Either maximum infinity or minimum, depending on the type of quadratic. And again, for a minimum quadratic, the maximum value will be infinite because it has no limit, because those 2 points just continue getting bigger for every time you move up an x value. So completing the square is useful. As I mentioned in video 2, completing the square is useful because it allows us to find the turning point, which therefore lends itself to helping us find the maximum value of a quadratic, because in that form we can identify the turning point, and therefore we can identify the value which it maximizes or minimizes depending on the type of quadratic equation that we have. So, example 1. What is the minimum value of the following function? F of x equals x squared plus 6x plus 11, and the x value this occurs at. This is really just a fancy way of asking for the turning point, but they're asking for it in the context of understanding that the turning point is the minimum value or maximum, and that can be useful for practical applications further down the line within the higher maths course and beyond. So try this question. Well, step 1, as I mentioned, complete the square is going to be useful, so we need to complete the square. It'll either be a National 5 level technique, or it could be the higher level technique. Either one could be asked in this type of question. So you complete the square, remember, drop the squared term, half the coefficient in front of the x, drop the x, put it in a bracket squared. When you do that, you'll get x plus 3 all squared. Again, you have to take account of an extra plus 9, so we're going to subtract 9. Simplifying the minus 9 and 11 should give us a complete the square form of x plus 3 all squared in a bracket all squared plus 2. At this point, we are ready to use the complete square form to identify the minimum. As you recall, a positive x squared parabola, because we know the equation is positive x squared, is the happy face. Just for kind of generic, that's not anything technical description, but it's a minimum turning point. So the minimum value would be at the lowest point there, therefore at the turning point. If it's a minus x squared parabola, it would be a maximum. So for our one, as I said, it's positive x squared, so therefore we're looking for the minimum. The minimum value will be the y coordinate of the turning point. From the complete the square form, plus 2 is the y coordinate. So therefore, our turning point is at minus 3, 2. The minimum value of this function will be 2. It will never go lower than 2. It will only ever get bigger. And this will occur when x equals minus 3. So it's basically just a way of stating the turning point, but doing so in terms of maximum value and when that occurs at. So it's just another take and turning point, but it's a more useful, maybe practical application, useful sort of way of doing it. Another 2 examples to try. Again, as before, we're completing the square. If it's not written in standard form, write it in standard form before you do anything to do with completing the square. That brings the minus x squared plus 3x plus 6. That means we're going to have to deal with the negative, take it out as a common factor, then do completing the square process, which should give us minus bracket x minus 3 over 2, all in a bracket squared. We're going to have to deal with a add or subtract. But as I said before, if you're taking a negative out, you've got to be careful that what we add is not actually going to be an add this time. what comes out of the multiplication of the bracket will not be an add this time because of the negative outside. So we're going to have to add it in order to get rid of it. So in this case, we're going to have to add 9 over 4, complete the square by adding the 9 over 4 and the 6 together to get minus bracket x minus 3 over 2 all squared plus 33 over 4. Now we complete the square, we can determine the maximum value and the x value this occurs at because it's related to the turning point. So therefore the max value of the function will be 33 over 4. It will never be bigger than that. Think it is a sad face, maximum parabola. So therefore once it reaches a particular y value, i.e. at the turning point, it will never go higher than that. And for this example will occur, this max value of 33 over 4 will occur when x equals 3 over 2. Example 3. Again, I'm just testing all the skills here. You need to take common factor of 2 out, both the x squared and the x term. That's allowing us to complete the square after that. Again, when you're completing the square, watch out for the plus 1. Multiplying by itself will give 1, but then it gets times by the 2 outside. So we're having to subtract 2 in this occasion, and that will create 2 bracket x plus 1 all squared minus 5. Again, we've now completed the square, so we can determine the minimum value because this will be the value of the turning point since it's a minimum parabola. So therefore, our minimum value is minus 5. And in this occasion, we haven't been asked when it occurs, so we just need to write minimum value equals minus 5. Now, example 4. This is getting towards the very hard end of a kind of maximum of a quadratic function. They have occasionally occurred in the past, but they're quite rare, but they could ask it, and this is a kind of test of your full true understanding of what's going on in terms of maximum. So example 4 is determine the maximum value of the following function, the value of x at which this occurs. This is a function within a function because you have the fraction, which you've got the 1 over, and then you've got the function x squared plus 4x plus 6 within it. So you've got to understand this is kind of a double function operating and will therefore affect how the result occurs for your maximum. Now, an exam tip. When a quadratic is on the bottom of a fraction, the overall function, so the 1 over with the quadratic part of it, will have a max if the quadratic function is the minimum type, i.e. a positive x squared. Or it will have a minimum, so the overall function, the fraction, will have a minimum when the quadratic is a maximum quadratic, i.e. a minus x squared. So for our example, we have a positive x squared quadratic. So this function, 1 over, will maximize when our quadratic minimizes. When does our quadratic minimize? Well, if it's a minimum quadratic, it will minimize at the turning point. So therefore, this question is asking us to find the turning point, but to realize that that will affect the overall function and it'll be a maximum. So it's like it's a maximum within the same question. Slightly confusing, I get that. So hopefully this explanation will work as I go through it. So, as I've said, the overall fraction will have a maximum when our quadratic is a minimum. We need to determine the minimum value of the quadratic part. So we just look at the x squared plus 4x plus 6 part on its own initially. So we look at that, we complete the square of it because we want the minimum value when that occurs, and it occurs at the turning point, which we get from completing the square. So we complete the square, so we get x plus 2 all in bracket squared. We're going to have to take away a positive 4, so we subtract 4, simplify it, and therefore we complete the square and therefore can read the turning point. So that gives us x plus 2 all in a bracket squared plus 2. Therefore, the minimum turning point of this x squared plus 4x plus 6 is minus 2. Therefore, its minimum value of x squared plus 4x plus 6 is 2. So it will never go lower than 2. So it can go higher, so it can go to 3, to 4, obviously the decimals in between, 5, 6. Now think about this. If we sub those numbers into the fraction, the bottom part, 1 over is that quadratic. So as that quadratic's y value changes, the bottom of that fraction changes. The lowest number it can be for x squared plus 4x plus 6 is 2. Therefore, that's a half. Now, if we move to x squared plus 4x plus 6 going up to 3, you'd have 1 over 3. Hopefully, you can see that a half is a bigger value than a third. Now, if we move x squared plus 4x plus 6 to 4, you'd have 1 over 4 as a quarter. A quarter is now smaller than a third. So as we go up the integer values of this quadratic, the fraction will keep getting smaller and smaller and smaller until it becomes an infinitesimally small fraction. So this fraction will keep getting smaller as the quadratic rises in value. And since it never goes below 2, we can stipulate that the maximum this fractional function will ever be is a half. Okay, and that comes from understanding what the quadratic part does to the overall function. So the function's maximum value is a half, and it will occur when x equals -2, because that is when the quadratic part of that function goes to its minimum value.